Hello AP Calculus students, this is Mr. Luya here, and in this video I wanted to go over example number 2, space shot, and this is found in your notes for section 8.3. I know that a lot of you were absent. I'm not going to say why. I would suspect a lot of you were skipping to go to the beach, but that's okay. I want to make sure that none of you fall behind, so that's why I am creating this video to make sure that we clear up any questions, because you probably might have trouble answering this question on your own. So now, of course, if you were here on the Friday before spring break, then you're not required to watch this video. However, there are a couple of things that I'm going to mention, specifically a question that Andy asked. And I'll see if I can answer that question in this video because I did look it up and I found an answer. So, example number 2, space shot. It says over here that the space shot is an amusement park ride that gently raises riders up a tower and then rapidly bounces them up and down using compressed air. The velocity of the space shot for the times between 0 and 14 is modeled by a piecewise linear function as shown below, where t is measured in seconds and v in feet per second. So you'll notice here that when we look at this graph, we're looking at the function v with respect to time, right? I know most of us are used to seeing the position graph, but you have to understand that this is the velocity graph, right? And most of us hopefully remember from Unit 4 that the velocity is essentially the first derivative of the position function. So just make sure you keep that in mind. And there's always going to be an FRQ, not always, but most likely than not, there's going to be an FRQ that has something to do with position, velocity, and acceleration. So if you look at part A, it says, at what times in the interval between 0 and 14, if any, does the space shot change direction? Give a reason for your answer. So hopefully you guys recognize by now or remember way back from Unit 4. This is a Unit 4 question, Part A. You know that the velocity is going to change when the direction is going to change when the velocity changes signs, right? So you'll notice here it changes signs right there, and right there, because from here the velocity is positive, which means it's either going, well, in this case, it's either going up or down, right? So if the velocity is positive, that means that the amusement park ride is going up. The second it falls below the graph, that means that the velocity is negative, which means that it's now going downward, and so on and so forth. So to answer this question, it's pretty simple. Some of us will probably say, oh, well, it's changing directions at 6 because it goes from positive to negative, changing directions at 8 because it's going from negative to positive, and changing direction at 10 because it's going from positive to negative. Yes, while that is a perfectly accurate answer and it's very detailed, you don't need to write that much detail on the AP exam. In fact, an answer just like this is good enough. At t equals 6, 8, and 10, because v of t changes signs at those times. I'll just continue it there. All right. This answer right here will give you full credit for the AP exam, and you save yourself a little bit of time and writing. So, and we all know that in these FRQs, we are limited on time for all the amount of questions that they ask us. So every second we save ourselves will be very good. So part B, it says, at what times in the interval between 0 and 14 is the space shot the highest? This is easily the most involved problem. So the thing is, the space shot is going to be located at different points depending on, where it is. Like, obviously, if the velocity is positive here, it's in the middle of moving up. But the second that it changes directions, that can be a viable option for where it could be the highest point, right? And if you remember back in the day when we used to do relative minimums and maximums, we would know that we have relative minimums and maximums at our critical values, right? And the critical values are where the first derivative changes from positive to negative or negative to positive, et cetera, right? So what we're going to do, we're going to have a different way of testing the position of those critical values, right? So we're going to obviously use, our candidates would be at t equals 6, t equals 8, and t equals 10. However, we don't really know, right? Obviously, we have an initial position there, and we have a final position right there, like the final time. You know what? We're going to go ahead and use those as candidates as well, because we don't know exactly where the space shot is located at those times. It's probably not going to be those times because obviously it's going to start at the bottom or end at the bottom. But still, we have to test those times out because, again, usually whenever they give you some kind of like interval, it's expected that you're going to test the beginning and ending interval. So that's what we're going to do. So I'm going to go ahead and list this out and say that our candidates are t equals 0, 6, 8, 10, and 14. Okay? So, of course, if we want to know when is the space shot the highest, we pretty much need to know what the position is, right? And you know, if we have our velocity graph, if we want to go from velocity to position, well, we're going to have to do some form of integration here. So that's what we're going to do. First of all, I'm going to integrate between between the time 0 and 0, right, of our position y of t, right, dt. Okay, I'm saying y, I don't know why I chose y as position, I guess because it's, you know, on the y-axis, along the y-axis, all right? So really the area under the curve between 0 and 0, well, of our position function is going to be pretty much 0. So it's likely not going to be that one. So now we got to say, okay, well, if the velocity was moving up, if we find the area between the times 0 and 6, that's going to tell us, you know, it's moved this amount between 0 and 6. So when we integrate this or find the area underneath this curve, that's going to tell us the position at 6 seconds. So if we do the integral from 0 to 6 of y of t dt, well, let's see what that's equal to. I mean, granted, we don't have functions here, but what we can do is we can figure out what the area of this trapezoid is, and that'll give us our answer. So hopefully we remember the area of a trapezoid. Hopefully when we that you're reminded of that when we did trapezoidal sums. It's going to be 1/2 times base 1 times base 2, so 6 plus 4. And then times the height, and our height here, we're at intervals of 20, so our height is going to be 20. Okay, so that is 100. All right, so the position after 6 seconds have happened, it's at 100. All right, well, what happens if we go from 0 to 8 seconds? Right? What is what is the accumulated total distance from 0 to 8 seconds of where it's located now? All right. So obviously this was an area of 100. But now the thing is, and this is a question that Andy asked in class, he's like, is it necessary to really calculate the position from 0 to 8? I mean, if it has a negative velocity, it's going to be, maybe after, I'm just going to draw a little figure here. Right? It starts down here at the bottom, but then the ride kind of moves upward and maybe lands at 100. But if there's a negative velocity, it's going downward. So wouldn't that position be lower than the 100 anyway? So what's the point of testing all the way from 0 to 8? And he's 100% right. You know that this candidate is not going to be the right option. But the problem is, and this is what I double checked with the AP community, the problem is, in order for you to explain that, you would have to give a justification for why you're not testing out 8 seconds. And in that explanation, you'd have to say, well, there is no point in testing out from 0 to 8 seconds because, and then you give them the entire explanation is because if the velocity is negative, then, you're subtracting a negative, you're pretty much subtracting the distance from the ground it is from that position after 6 seconds, so on and so forth. And they said that you would have to give an explanation. However, if you just did the quick little interval, that would be just as good of an explanation. So I'm personally going to go ahead and just work out the interval simply because I want to save myself some time and not sit there and justify why I'm not testing out 8 seconds. So you cannot just ignore that 8-second candidate. All right. So from 0 to 8 seconds of y of t dt, right? We know that we have, let's see, it was the original 100 plus, right? We got to include the area of this triangle. And really, we're subtracting, but I'm just going to put a plus and put a negative somewhere in there. So the area of this triangle is going to be 1/2 times the base of 2 and the height of negative, let's see, that is negative 60. I just think my paper didn't print out the grid very well, but there usually is a more defined grid there. So 1/2 times 2 times negative 60. So that's going to ultimately give me a negative area there. And so I end up with 40. So after 6 seconds, it's at a height of 100. After 8 seconds, so 2 seconds later, it went down. Okay. Sorry, I had a phone call. Hopefully that didn't interrupt it. So after 2 seconds it went down 60. So now the new position after 8 seconds is at a position of 40 feet. So let's go ahead and test out the other one. So we have the integral from 0 to 10. So now we're going to continue off from where we were before, 40 plus, my notation's wrong, of y of t dt is equal to, let's see, we have 40 plus, and then we got to find the area of this triangle. It's going to be 1/2 times the base of a distance of 2 and the height of 40. Right, so that's just going to be 40 plus 40, which is 80. We also got to find the position from 0 after 14 seconds of y of t dt. And that's going to be equal to our previous 80. And then we're going to end up subtracting. So I'm just going to say plus 1/2 times a base of 4. That height is negative 40. So all together, let's see, that's going to be 1/2, that's 2 times negative 40 is 80. So it's going to go right back down to, which makes sense, after if the ride is 14 seconds long, which is a pretty short ride, but after 14 seconds long, it went back down to its initial position. So after careful analysis, we can see that our winner is after 6 seconds. So it's just pretty straightforward from here. So we're going to say the ride is at its high, let's see, is at its highest point, right, at t equals 6 seconds at a height of 100 feet. Okay, pretty straightforward. All right, so let's look at the next part. It says, find the total distance of the the space shot travels during the time interval from 0 to 14 seconds. So ultimately, hopefully you guys remember, by now, that if I just integrated the absolute value, right, of all of this entire function, so if we integrated the absolute value of v of t from 0 to 14 seconds, dt, then that's going to give me the total distance traveled, because yes, from here, so I mean here we established that was what was that? That was negative 60. This one ended up being let's see, positive 40. This one, so I'm just going to put plus 40 plus 100. This one ended up being minus 80, right? So yeah, the net displacement, right, from 0 to 14, it went up 100, then down 60, then up 40, then down 80. It went down to 0, right? But if we're talking about distance, right, we're thinking about the total distance traveled, whether it was up or down. So really, we would have to do 100 plus 60 plus 40 plus 80. So that's going to equal 100 plus 60 plus 40 plus 80 for a total distance traveled of 280 feet. All right. Wow, this video is longer than I wanted it to be. We're at almost 14 minutes here. So for part D, it says write expressions for the ride's acceleration a of t, velocity v of t, and distance s of t from the ground that are valid for the time interval from 10 to 12. So right now, we're only interested in this time interval from, what the heck, my pen is all messed up right now. Here we go. From 10 to 12. This is what we're interested in. Okay, so this actually doesn't end up being too bad. So let's go ahead and start off with the acceleration first. So we should understand that the acceleration is pretty much the next derivative of this function right here. And wouldn't the next derivative pretty much be the slope of that region? So in order to figure out what the function for acceleration is, all we need to know is, well, what is the slope of this? So hopefully we know rise over run. So we know that it's not rising up, but rising down, or I guess depressing down, a distance of 40, and then running a distance of 2. So our acceleration is going to be down 40 over 2, or negative 20. So that one was pretty simple. Now, if I want to know what the velocity is, right? Well, the velocity at any point over here, the thing is, do they want to know what is the velocity of, you know, time, like maybe 10.5, 11, 11.5? I mean, how do I know which time that they're interested in knowing what the velocity is? So if what they essentially want you to do is they want you to write an expression for the velocity, right? So we want to come up with kind of pretty much what the linear function would be. So this isn't even a calculus problem. This is more of an algebra, like an algebra 1 problem, really. I mean, we have 2 points here between the line. We have 10, 0. We also have 12, negative 40, right? So, I mean, I guess we could pick a point, figure out what the slope is, which, well, we do have the slope here. So all we have to do is figure out like the point slope form. So we have y minus, I'm going to pick the 10, 0 just because that's much easier to work with. So I'm going to do y minus 0 is equal to the slope, negative 20, times x minus 10 right there. So when I work this out, I get y is equal to negative 20x plus 200. And there you go. That's going to be our velocity function, right? Negative 20x plus 200 for t equals 10 to t equals 12. Okay, so if I wanted to know what is the velocity at time t equals 11, I could just plug in 11 and I get my velocity function. So there's my velocity. I'm just going to write this over here so that it's next to each other. Negative 20. It's an obnoxiously large negative. Whatever. All right. Now for the position, though. So remember, in order to figure out the position at any one of these points, right, we essentially... This is the more complicated one because we essentially had to integrate whenever we wanted to go from velocity to position. So I know that I'm going to integrate, right, from, so I'm going to leave some space here. So our position function, or I should have said y, whatever, is equal to, let's see, the integral. Now I wish I would have, I'm not going to start this video over, but essentially, we need to know what the position is after 10 seconds in order to know what the position is after all of this. Because the thing is, if we only integrated from that region right there between 10 and 12, well, that's going to tell us how much it moved, you know, after 10 seconds. But it kind of was already at a position at 10 seconds. And that position, well, we kind of already calculated here, was 80, right? So we would need to start this off. It starts off at a position of 80, then plus, right? And then if we want to figure out like any kind of generic area, again, do we know if we want to know the area from 10 to 11, like after 11 seconds, 11.5 seconds? Those are going to give us different areas depending on what, you know, what time you're looking at. So what we're going to do is we're going to give them kind of a more generic integral, right? So I'm going to say, so starting from 10 seconds to, honestly, I don't really even know, some value t, right? And then I'm going to go ahead and put v of, I guess I'll put x for now, dx. I mean, if you put t or dt, don't worry, I asked this from the AP community. They said that they would accept this answer, but it doesn't make sense to put t there because, I mean, we're already defining t up here. So if we integrated this, we're plugging in times into that function. But again, if you put v of t dt, that's perfectly fine too. And this right here is the correct answer. Okay, so this will tell you the position or the generic expression of the position for any time between 10 and 12. And this is only valid for that region right there. So I'm going to go ahead and leave it at that. And hopefully that was helpful for you guys. And that's, I mean, this problem, I think we also finished the previous problem. But I think this was the more important problem. You can always just grab the notes from someone else if you weren't in class that day. Either way, hopefully this was helpful. Hopefully you understand it. If you have any questions, of course, feel free to ask me, and I'll see you guys in the next video. Take care.